Right. Am I audible now? Hello? Okay, right. Thank you. Thank you for letting me know. Right. So the idea is that there is a synchronous generator and it is connected to a bus bar, right? And it is represented by voltage and angle delta. So I hope you are familiar with complex numbers and their representation. Are you guys familiar with complex numbers and their representation? Okay. What about you, Mahak? Okay, cool. So you do know that there is you can represent this number as a plus ib or right. Okay, so there are two possibilities. These can be used interchangeably. So in power system we tend to use polar coordinates a lot, right? So this is how we represent that in one line diagram, right? Now in with respect to react. Okay. Yeah, I'm audible. Okay, I'm audible. I'm good. Okay, so then so there is also one more aspect when it comes to a synchronous generator. It's usually so it's you know that it is three-phase connection, right? So it can be any three-phase connection can have two possibilities. Either it is star connected or it is delta, right? Usually for generators, we always prefer star connection because of the presence of neutral and so that we can extract each phase separately, right? So when it comes to the neutral, there are different possibilities. It can be connected to ground, right? This is called a solid grounding. It can be not connected to the ground. It can be just like left open. It's just like can be just a simple three phase, or it can be connected to ground via it can be connected to ground via a reactance or a impedance. So it's called as impedance grounding. We will look at what these all are um, when we talk about protection, because so basically um, this different types of grounding plays an important role in protection. So we will look at it when we are talking about protection, right? Uh, just give me a second. I think my audio is going away every now and then. Just give me 2 seconds to fix it, okay? And I'll be back. Are you guys able to hear me now? I hope I am audible, right? Okay. Okay. Right. Okay. So now let's look at how the react, reactance diagram looks for a synchronous generator. So as we said, it is a voltage source in series with a reactance, right? So what we do is that we draw a AC voltage source connected to ground. Okay. So this is the reactance, and this will be the angle delta, right? So this is how the reactance diagram for, and this will be the terminal. This is how the reactance diagram for a synchronous machine looks like. Next, let's look at the other important device in power system, which is the transformers. Okay, sorry, this my somehow my system just locks my mic out. Okay, okay, I'll be a little more careful about this. Right. Okay. Um. Okay, so it could be so there is usually the representation of what the transformer connection is. It could be star star. It could be delta star. Could be star delta or delta delta. Again, when we're talking about star, there are different combinations that are possible, like with respect to grounding. So there are different types of that also will come into picture, right? And sorry, and the reactance diagram representation is a single, right? And this is with respect to neutral, right? Then the representation, this is for transformer. Okay, this is for the transformer. Then let's look at the representation for transmission line. So going forward, if I write something like P bar L, it is transmission line. Okay. So for transmission line, the one line diagram representation is one straight plain line, right, with two terminals. And the one line diagram representation will be same as transformer with XP, right? So that is the transformer, right? Um, then for a load or an induction motor, can think since we have space here, let's look at an induction motor or any any load is by C. These all are series components. So it is between 2 points on the so at the end of the day it is connecting between 2 points on the face. Usually loads tend to connect between force, phase and neutral, right? So an induction motor is usually represented as um, this is one it's not a standard representation, but yeah, there are multiple representations, or it can be represented as a just like a motor itself or a synchronous machine itself. And the way it will look is this is neutral and this is phase, right? Is that clear so far? Is that clear so far? All right. Okay. Great. So now let's look at how to draw a reactance diagram for a transformer. Okay, let's look at this situation that okay, I have a generator connected to a bus bar, which is connected to a transformer, which is connected to a transmission line, and which is again connected to a transformer, which is connected to a motor. Okay, so yeah, pardon my drawing, I'm not that good at drawing, but still. Okay, so let's I want you to individually draw the reactance diagram of uh, for the system. Can you try drawing the reactance diagram for the system on your paper or whatever paper or this thing you have? Can you give it a shot? And just let me know how it turned out. So this would be T1, T1, TL, T2, and 1. So I'll just start drawing here so that you can, I hope you guys are already started drawing. T1, T1, right? Then it is connected. This would be T1 and connected to so were you guys able to get this, or were there any confusions? Okay. Okay, so I'm taking S means you were able to draw this, and no means you were not able to draw this. Is that how it is? So Varun and Mahak, you were not able to draw this, right? Right. Okay. Uh, so if you okay, Varun, what do you think it went wrong for you? Okay, good. Okay, fine, cool. So that was me. I framed two contradictory questions all together, and that confused it. Okay, fine. I'll try to be. So this is a little more confusing because I can't see you guys face to face, and I don't know exactly what. Okay, fine. So. This is good, right? Okay. Now let's revisit. So this is the concept of reactance diagram. Okay. Now let's revisit the concept of uh, per unit quantity, right? Okay. Right. So right. And so we know that per unit quantity is actual value in units divided by base value or reference value in units, right? So in the last class, I think Dharani was not there. Just for your sake, I'm just doing a quick recap. What we'll do is that we will decide two quantities that okay, we will select voltage base and we will select a power base. So we will select these two values, and based on those two values, we can calculate the current base and the base impedance, right? So we will select these two and we will calculate these two. So in any given okay, so in any given system, we will get the ratings of the system or machines or the equipments that we have. Then we will select a value as our base values, and then we will divide the given values by these base values so that we will get these values in per unit quantities, right? Uh, so just one quick recap. What did we calculate as set base as? Set base is equal to P base the whole square divided by P base. I hope you guys remember this, right? So okay. So just a quick recap, just to make sure that you guys remember what we discussed in the last class. So I'm talking about an alternator, right? So we have an alternator rated 200 MVA, 13.2 kV, right? And X is equal to 6 ohm, right? So question is, what will be the PU reactance at 400 MVA base and 18.2 kV kV. Okay, so can you guys calculate this and let me know? Are you guys able to do it? Mm-hmm. So okay, we have answer number one as 6.312. Okay. Okay. So we have two answers. Yeah, take your time. Take your time. Okay. So three answers for 6.312. Okay. So now we have two. We need two more votes. I think Sridevi and Dharani. Okay. Okay. We have a different answer. 7.24. And okay. Then if you have any problem, just let me know. Okay. Anyway, so are you still trying, or do you want? Shall I start solving? Okay. Okay. It's four people versus one. Okay. Let's see where it goes. Okay. So what is this one? It is X ohms divided by basics, right? So what is basics here? 18.2 the whole square divided by 400, right? So okay, so that would be 7.24. So the correct answers are actually 7.24. So this is the correct answer. So where did you guys make the mistake? So the thing is that you have to be very careful about questions in GATE. What they tend to do is that they will overwhelm you with a lot of information, right? So you have to be careful about what is the information that they have provided. So they have provided the rating of the generator, but they have given excess ohms. They did not give excess per unit, right? So did you guys use that? Okay, now the question, if I add an extended, okay, is that clear why that is 7.24? Yeah. So you probably did you use that other formula where base kV old divided by base kV new the whole square thing? Right. So if there was an extension of this question, okay. So if there was an extension to this question, right, where it says 'I'm adding one more question, second part. Calculate XPU in generators space, right? So there are two approaches again over here right now. First is that we have already calculated the so the answer to the first part was 7.24 pu, right? Now can you do the second part? Again, second part there are two approaches, right? We'll look at both. Okay. Can you tell me what the answer for the second question will be? The first approach is to use the same approach that we used for part 1. That would be to calculate base impedance as 13.2 the whole square divided by 200. Also, don't see, just because I'm doing this directly, this is because I'm aware about always be aware about the units. So here it is 13.2 kV and 200 MVA. So 13.2 the whole kV whole square will be, there will be 10 power 6 over here. And denominator also there is 10 power 6. So in my mind, I am aware of this fact. That's why I'm canceling this over here. I'm not writing it. But always be careful about this, okay? Because this unit can, so if they give us, sometimes what they do is that as a trick thing, they'll give you it as 200 kVA. So you will go by this pattern and you will end up making a big mistake, right? So don't do that. So that is the approach number 1. So this would come as we can always use that formula. X new is equal to X old into V old divided by P new the whole square into P new by P old, right? P new by P old. Yeah. So if I substitute this over here, it would be 7.24 into 18.2 divided by 13.2 the whole square into 400 divided by 200 divided by 400, right? Divided by 100. So if you also do this, you should get 6.88, correct? Are we good? All right. Okay. All right. Shall we proceed to the next concept? Okay. So the next concept is this is kind of an interesting thing. It's like a statement. Let me see. So the statement that I'm going to make can be or can be wrong or can be right. Okay, it can be right and wrong. I'm just trying. So just let me know what your thought about this is. So so earlier I showed you how we represent a transformer, right? So one thing that I want you to, yeah. So probably one thing that you notice is that just two circles. So this is supposed to be two circles. So one is small and one is big, right? The idea is that this will be the higher voltage side. The bigger circle will be the higher voltage side, right? Mm, right. So if you look here, this is primary side. Okay. VP, VS. So can you tell me what kind of transformer this is? If I'm giving you that smaller circle means lower voltage, higher second voltage means bigger circle means higher voltage, then yeah, it's a step-up transformer. Good. VPVS. Good, good, good. VPVS. IPIS. Okay. Right. So tell me, according to this, let me take two colors, and you tell me which is the correct. So which is the correct relationship? Right. Mm-hmm. All right. Mm-hmm. Actually, technically speaking, it is neither, to be honest. Problem comes over here. It's basically set P is not equal to set S. It also depends on the construction that whether primary or secondary has higher impedance. So let's think about this. Um, okay. One just one more thing. Just let me know what is the relationship between. All right. Right. So most of you said that it was blue, but again, this relationship, the actual correct relationship is set P not equal to set S. Whether primary impedance will be greater for a step-up transformer is a thing to be thought about. Probably when we are going to the next step, we will look at it. I just want to have one more poll with you guys about the relationship between PP and PS, right? So I'll just give you custom poll. Yeah, so there is one more. Mm-hmm. Mm-hmm. Okay. So, right. This is this is an interesting set of answers. Okay. So what I want to know here is that probably all of these answers are correct, but I want to know what is the justification behind it. So for people who assumed that PP is equal to PS, can you tell me what is the assumption that you are making? So this is something that I keep on telling you, probably even if you watch the previous gate questions video, always ask yourself what are the assumptions when you're making a statement. So every single option that every single answer that you have given is right if you state the correct assumption. Can you tell me what the correct assumption is for the people who said it is equal to?
Sir, I guess it is none because we don't know what Z is. Since Z is not equal, assuming, yeah, I squared Z or something like that, PP and PS depends on the design.
Okay,
So I think
okay,
we can't say what happens.
all right. Okay, that is the none answer for none.
Yeah,
Okay,
yeah, okay.
continue. For the people who gave me the answer equal to, what is the assumption? Mm, I think. Okay. Okay. So the shall I go ahead? Okay, let's see the possibility that PP. Okay, so just to clear on that part, what Sridhi was saying, that the idea of a transformer is that transformer is a device that does not per se use consume power. What it does is that it steps up the voltage or steps down the voltage. It on its own should not consume power. So in an ideal world where there is no losses, in an ideal world where there is no losses, PP will be equal to PS, right? So the assumption over here is that no loss, right? And if I have to say PP is greater than PS, the assumption is that there is loss, right? And the justification for me to say PP is it is none, because the exact or the correct exact this thing would be PP will be always greater than or equal to PS. So it is a combination of these two. So this is probably the correct expression, because transformer, the primary side and the secondary side power are should be same, but if there is if we are assuming that there is system losses, if there is I square R losses, if we are assuming, doesn't matter whether set P or set S are equal or not. That's got nothing to do with it. It's whether we are actually considering set S equal to R plus Jx, and whether this R can be ignored or not, right? So when you're talking about electrical machines, probably transformer is one of those machines that is high, that has the highest efficiency. It has the efficiency about 95 to 98%. So the losses are almost negligible. So when we are usually looking at problems, the assumption that we are going for is Vp is equal to Ps. Is that clear? Vp IP is equal to Vs. Again, the question is whether you are ignoring losses or not. This is with the assumption that the losses are ignored. It should be Vp IP is equal to Vs plus I square R, or I square R, or whatever that equivalent is. It will be IP square Rp plus I square Rs, right? Okay, so now again, I have this habit of diverging. That's okay, but it's good to have your concepts clear. So the statement that I was about to make is that, so we just said that set P is not equal to set S. So this is with respect to ohms. But what I'm going to say is that now XP per unit is equal to. So do you agree with the statement, or do you think this is wrong? So the thing is that, see, I could just keep on stating facts, points over points, and keep on going forward. I could just, whatever I did this in the last two slides, I could just do it in a minute and say, okay, this is the thing, just take it. But I want you guys to think. So that's why I'm just taking a little time over here. So I would rather prefer if you guys can get back to me a little quickly, because if it were a class, it would be easy. Okay, I'll start a poll for this one also. So do you think this is true or false? All right. Wow. Takura, Varun, do you have any responses? Okay. All right. And this, so the majority is saying that it is false. So according to the majority, it should be right. So this is what is according to the majority, but this is wrong. This is right. So this is one of the most beautiful aspects about one line it's per unit system. That's why we are finally able to represent a transformer as X per unit as a single reactance, because the primary side and secondary side, when it. So what will be set primary prime? That will be set P ohms divided by set base, right? So that would be what? Set P ohms divided by Vp the whole square divided by P, since P on both sides are same, right? So that would be set P ohms into P divided by Vp square. Correct? Are you guys with me so far? So if I do this would be set P ohms into Vp divided by Vp square. Correct? So this would be okay. Yeah, so then let's look at this. Let's look at what is Z is PU. That would be Z is ohm divided by Vs square into P, right? Okay, and now the question arises, what is Vs square, right? That would be Z is ohm into P into A square V square, right? The derivation does not look good in my paper. Set P and set base V square Mhm. Okay, so that is derivation is the derivation that I have somehow does not make sense to me right now. We'll just try to derive this fresh, right? Um, okay, so what is what would be ZS? ZS would be VS by IS. Does that make sense? It does make sense. Okay, so it would be VS by IS into P divided by A square PP square, right? So this would be KVP divided by IP by K into P divided by K square PP square, right? So the K square gets cancelled. It would be VP are you guys able to follow up to this point? Is that clear? So this would be VP by IP. Wait, we'll get back to the derivation. For now, let's just okay. I don't want to spend too much time around here. We'll come back to the derivation. Probably I'll just write down this notes. It's a little huge derivation. I'll just write down in notes and give it to you. So for now, this is just hold this as a fact. I'll come back with the derivation. Is that okay? Are you guys there with me? Okay, right. Sorry, I just made it a little confusing over there. I'll get back to the derivation because the derivation somehow I'm losing some fact over there, and the note that I have is not clear. Right? Mm, okay. So now let's look at one question. Okay. So the question goes like this. Right. So we have a generator. So this is an alternate representation of a transformer. Okay. Transformer. Again, a transformer, and it is connected to right, and the values are given to you. So we have the generator values is given as 150 MVA, 13.2 kV, and X is given as 2 per unit, right? Then for T1, this is transformer 1, they are given as 100 MVA, 11 bar 121 kV. Yeah, for so this is given to you, and right. So the first thing is to calculate. The idea is to draw the single line diagram or the reactance diagram for this, marking the correct PU values. Can you guys give it a try? So there is okay. Can you guys tell me what OHTL is? What OHTL is the abbreviation for? Correct. Overhead transmission line. Right. So before we proceed, can you tell me, just I want you to, so this is a mistake that a lot of people usually tend to make. So just want to go ahead and tell me what is the values for first let's start with what would be VB1. We are starting from that side. VB1 would be, let me see. Okay, I'll put this one for you. VB1 would be 15 kV. The base value will be same as this one. But whenever we encounter a transformer in the one line diagram, VB also has to be shifted to that value, right? So here it would be, the V base would be 15 into 121 divided by 11. What is the value? That will be 15 divided by 11, right? So 15 into 11. 165 kV. And again, we come, then we encounter a transformer, and this transformer is 121 bar 5.5. So this would be whatever the base value was there at point, 1665 into 5.5 divided by 121. Any doubts? Is that clear? Does that make sense? Okay, so let's try to do the calculation, right? So for a unit in the new value, it would be 2 into the base kV old is 13.2 divided by new is 15 into the new is 200 divided by 150. Is that okay? Oh, sorry, it is not okay. Right? Comes as 7.5. Okay. Okay, so I don't have my calculator handy, so you got this as 2.065? Yeah, 2.06, correct. This is 2.06 u. And also always not to forget, this is J 2.06 per u, okay? Because we are talking about X, right? So the next thing that we need to calculate is X T1 per unit. So what is given? It is given as 1.2. So that would be 1.2 divided by 13.2 divided by 15 the whole square into 200 divided by 100. Okay. Oh, sorry, my bad. 11, correct. 11. Was carried out. Thank you, Sridhar, for that correction. You can also take it as either 11 by 15 or 121 divided by 165. Both are correct. What is the value that you're getting? Yeah, 1.29, correct. Thank you, Thakur, sorry. So if I'm pronouncing anybody's name wrong, just let me know, because I'm just going by the sound of, because English is a non-phonetic language, and given the spelling, I am just spelling it with respect to my mother tongue. So there might be mistakes, pardon me. Okay. Okay, so now we need to calculate. Right. So how do you calculate for XOHTL? Tell me. I'm listening. So what are we given? We are given 60 ohms. So XOHTL per unit would be 60 divided by. Tell me, what should we be? All right. Can I get other people's opinion as well? Come on, guys. Let's rush it. Give me an answer in 10 seconds. Okay. Good. 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 So almost people who have answered in the given time has given the correct answer. It is 165. That's correct, right? So it would be, again, it would be 60 into 200 divided by 165 square. Again, I am again and again I am telling you this. I am doing it directly because I know that the 10 power 6 and 10 power 6 will get cancelled. If you are not confident about that metric, always write it as 200 into 10 power 6 and 165 into 10 power 3 the whole square and expand it. Okay. So what do you get this as? What happened? Okay, all right. It is correct answer is J 1.129. So just see, the problem is that I can't come. I don't know if you guys are able to find the answer or if you're struggling with the answer. If you are struggling with the answer, you have to let me know. There is no other way for me to know it. Okay. So you always have to let me know. Otherwise, this is going to be because this is more or less like a radio setup where I'm just keeping on talking and showing you things. But unless and until, so see, I know that some people are getting the answer and they are letting me know the correct answer. But if you are struggling to find an answer or if you are finding it difficult at some point, you have to let me know, right? So that I can help you, right? Yeah, so the last one is 1 into 3.3 divided by 7.5 the whole square into 200 divided by 55. So there is no confusion why this is 7.5, right? I think this should come as 0.44. No, it should come as 8.56 or 516 or something. 0.56 or 516 if I'm not wrong. 0.516. All right. So now let's draw the one line diagram. Sorry, the reactance diagram, right? So how would it look like? We have a generator in series with a transformer, in series with a transmission line, in series with another transformer, in series with a motor, right? So we calculated this as J.51. We calculated this as J1.29. This also we calculated as J1.29. And this one we calculated as J.44. And this one was J2.06. Now what you have to tell me is what is the value of E1 and E2. Can you tell me what is the value of E1 and E2? I'll go back to that first slide so it is easy for you guys. Tell me what E1 and E2 is. That is correct. That is 0.88 per unit, correct? And this one I think will come as 0.44 per unit if I'm not wrong. All right. So is this clear? Is this good? Because this is a very complex example where we are switching the base voltage levels, where we are actually getting the per unit values for all generator, all the type of units. We have different voltage levels, different these things. So are you guys able to solve this problem? All right. Okay. So do something. You guys are working with your laptop or this thing, right? So what I'll do is that I'll give you a question. Uh, Take a screenshot of it and keep it, and probably solve it for the next class. Right? Yeah. So take a screenshot of this, keep it, right? Yeah, just let me know once you guys have the screenshot. Solve it for the next class and see if you're able to do it. I'll also take a screenshot for my reference. Are you guys now comfortable with the idea of a per unit? Right. So that is about the what you call as um, graphical representation of power system. Right. Now let's look at mathematical representation. So let's look at the mathematical representation. And the mathematical representation, we usually tend to go for something called as bus admittance only has one T. That was a spelling mistake. Okay, bus admittance matrix. So we all are familiar with the concept of resistance and reactance and impedance, right? So basically, when you're saying V is equal to IR or IZ, right? This is the resistance term. So basically, whatever that term is, this is equal to V by I. Its inverse, that is Y is equal to I by V, is called as admittance. All right. All right. Okay. So that is called as one line diagram. So let's look at a one line diagram of a system, right? So we have three nodes, okay, and there are three transmission lines connecting. These are supposed to is there a problem, Mark? Okay, so basically, is it okay? Am I audible now? I'm audible now, right? All right, cool. So here's my notes. I think that will be easier. Wait a second. Okay, right. So this is considered as bus number 1. So this is considered as bus number 1, or in our terms, this is node 1, this is node 2, and this is node 3. Finish this off. So each line, so we are considering, I think, a short transmission line. So each transmission line has its own resistance and reactance, right? So this would be Z12, would be Z23, and this would be Z13. Okay, and there would be, this would be, the voltage at this node is V1, voltage at this node is V2, and the voltage at this node is V3. So the current injected to this node would be what? I3, and the current injected at this node would be I1, and current injected at the node is I2. So basically what we are assuming is that the current injected into the system is positive and current drawn from the system is negative, right? So that will make the power injected into the system being positive and power drawn from the system negative. So basically generation is positive and load is negative power injection, right? So individually there will be current through each branch, right? So what can we say right now? So okay, applying, okay, wait once again. So this is the current flowing through this one would be I13, and this would be I12. Okay, so now see, this is where I keep on telling you that this power system is all about a combination of physics and your network theory and electrical machines. So right now what we are going to do is that we are going to borrow a concept from uh, your network theory, which is here. So can somebody tell me what KCL is? Hello? Hello? It is Kirchhoff's current law. Tell me what that statement is or what that means. Yeah. Basically, current entering and current leaving a node is always zero. So if I apply Kirchhoff's current law at node 1, it would be I1 is equal to I12 plus I13. Right? So look at it. I1 is equal to I12 plus I13, right? So what would be I12? It would be basically V1 minus V2 divided by Z12 plus V1 minus V3 divided by Z13, right? So this would be V1 minus V2 into Y12 plus V1 minus V3 into Y13. Please note here it is small y. Small y represents the admittance of the line between Y12, and this one represents the admittance of the line between Y13, right? So if I okay, so if I rearrange and write it, it would be I1 is equal to it would come as Y12 plus Y13 V1 plus minus that will be minus Y12 V2 minus Y13 V3, right? So this, if I am going to represent it as a matrix, this is Y11 V1 plus so I would get minus Y12 V2 minus Y13 V3, right? So this, if I am going to represent as a matrix, it is Y11 V1 plus Y12 V2 plus Y13 V3. So all these are capital terms. So capital Y represents element of Y matrix. All right, and small y represents admittance of line. So this is kind of important. Please note. Okay, is that clear? So if I write equations for all the lines, all the current injection, I will get uh, so I will get something like this: I1, I2, plus bus admittance matrix, right? And this is called as bus admittance matrix. Where so basically this is how you derive it. So this matrix can represent actual grid connection, right? So where you can say capital Y I. So diagonal element will be sum of all the Yij where j is equal to 1 to n. So basically you see which all lines are connected or what all elements are connected to that node, find out their their admittances and take the sum of it. That is your Yii, the diagonal elements, right? And capital Yij will be is equal to minus Yij. Yeah. So this is called as, so see what happens is that in question they may not say Yii, they will say self admittance. All right. And this is total self admittance of I, and this is total mutual admittance of I and J, of line between I and J. Is that clear? Is that clear? Okay. So what we'll do right now is that we will stop here and we will come back and we will pick up on Y bus. We will do problems and we will look at Z bus building algorithm, right? Then we will be done with the representation. Then we will go to concept of power generation. Is that okay? Because as an engineer, it is always first an important aspect to understand how do you represent the system that you are working with. So we are done with graphical. We will finish mathematical in the next class. There are two representations. One is admittance matrix and impedance matrix. We will finish that and then we will go to concepts. All right. Any questions about today's session? So yeah, so I think that's it for today. So if you have any questions during this week or anything, you can reach out to me or you can save it for the next class and we will start it. We'll address any questions that you have at the beginning of the class and then we'll proceed with it. Okay. So yeah, have a good weekend and all the best. Right. Am I audible now? Hello? Okay, right. Thank you. Thank you for letting me know. Right. So the idea is that there is a synchronous generator and it is connected to a bus bar, right? And it is represented by voltage and angle delta. So I hope you are familiar with complex numbers and their representation. Are you guys familiar with complex numbers and their representation? Okay. What about you, Mahak? Okay, cool. So you do know that there is, you can represent this number as a plus ib or, right? Okay. So there are two possibilities. These can be used interchangeably. So in power system, we tend to use polar coordinates a lot, right? So this is how we represent that in one line diagram, right? Now, in with respect to react, yeah, I'm audible. Okay, I'm audible. I'm good. Okay, so then, so there is also one more aspect when it comes to a synchronous generator. It's usually so it, you know that it is three-phase connection, right? So it can be any three-phase connection can have two possibilities. Either it is star connected or it is delta, right? Usually for generators, we always prefer star connection because of the presence of neutral and so that we can extract each phase separately, right? So when it comes to the neutral, there are different possibilities. It can be connected to ground, right? This is called a solid grounding. It can be not connected to the ground. It can be just like left open. It's just like can be just a simple three phase, or it can be connected to ground via it can be connected to ground via a reactance or a impedance. So it's called as impedance grounding. We will look at what these all are um, when we talk about protection, because so basically this different types of grounding plays an important role in protection. So we will look